So it is about 5 o'clock, at least here in Trieste in the afternoon. Hello and welcome back, everyone, to the second session of this online workshop. I say hello back to those who are also here in the morning, but I can imagine that especially people from the Americas probably only tune in now. So let me just again give a little description of what we have in mind. So those who, because of time zones and so on, missed the two talks this morning, you can find those talks on the YouTube channel, to which there is a link, in fact, on this workshop's webpage. So you just go there, you click on videos, and then you can rewatch the talks of this morning. And obviously, while watching a recorded talk, you cannot ask questions. So this is why we have, at a later stage, these question and answer sessions. Like tonight, after the two talks, we will have Claudia Draxel, who was the first speaker this morning, and she will be here to answer some questions. So the idea is, who misses a talk can watch it at a convenient time later on YouTube, and then still have the possibility to ask some questions online. For those who are directly with us in Zoom now, you can obviously ask questions while the talk goes on. You just type it into the Q&A section of Zoom, and Nicola and myself will try to answer or to give them to the speaker. So this is how it worked this morning, and I hope it will also all work quite well this afternoon. Okay, so our first speaker is Oleg Breshto from the University of Southern California. So Oleg is a name who is very closely attached, in fact, to the field of excited state and excited state dynamics in semiconductors. For example, I remember very well, for me, it was a very important paper when I read it. It was, I think, in 2005 or so, about surface hopping calculations in semiconductors. That was a very, for me, the first time I came across Oleg. In the meantime, so his name, as I said, is very much linked to this whole topic of this workshop. So we are very happy to have Oleg here. And we're also happy that he got up very early this morning, because in California, it's still very early while we are in the afternoon. So thank you very much for being here with us, Oleg, and the floor is all yours.
Yes, thank you, Ralph and Nicola, for the introduction and for the invitation. It's actually great to be part of a scientific community, because here in the US, we're still very isolated and have to stay at home most of the time. I've only been to office once since the virus started. So thanks a lot. So I'm going to share the screen and set it up. Give me a second. So the topic of my talk is discussing the methodology that we developed to perform simulation of various nanoscale materials. And then I'll go over a few applications. As Ralph was saying, all questions are very welcome. So there will be 4 parts to my talk. The last part pretty brief. And after each part, I'll make a break to see if people have any questions. So what we do, we for a while have been developing a pretty unique methodology that combines something that chemists have done, and my background is more in chemistry and a little less in physics. In chemistry, people have been developing this technique called non-adiabatic molecular dynamics, starting from the 60s, focusing on the processes in gas phase or on surfaces, maybe in vacuum. But these days, people work on materials mostly, and that's why we combine non-adiabatic dynamics with real-time TD-DFT. Then I'll talk about quantum dots, which is a bit of an old story with some new additions, but it's a classic example of nanoscale material, because basically nanoscience started with the people suggesting that if you make crystals smaller and smaller, you would make something new, which they called quantum dots. And then I'll talk about metal halide perovskites, which is a very popular material these days for solar energy and other applications. And then I'll talk a little bit about 2D materials. So the question is how to model a system that's composed of atoms and electrons, cores, nuclei, and electrons. And you would like to do it in real time. And this is especially important from the times when I was doing my PhD, when people started to use lasers extensively in fields like chemistry, physics, material science, because you would like to mimic what happens with materials exactly in the time domain and at the atomistic level to mimic those experiments. And the simplest way to couple quantum and classical dynamics, and you would like to stick to classical mechanics to description of atoms because they're heavier and classical mechanics is much simpler. The simplest way to couple quantum electrons to classical atoms would be to use Ehrenfest type dynamics, which is based on Ehrenfest theorem, which goes back all the way to the beginning of quantum mechanics, which tells that the equations of motion for quantum mechanical averages are exactly the same as classical equations of motion. Of course, when you write some expectational value of a force operator in quantum mechanics, it's not exactly the same as force in classical mechanics because you cannot evaluate the force just from the average position. It's a separate variable, separate observable. But formally, these equations look very, very similar. And therefore, it's straightforward to take some quantum expectation value and then put it into classical equations of motion. And this is the origin of the Ehrenfest theorem and Ehrenfest approach to quantum classical dynamics. This method can be derived in many, many ways. Initially, it was first introduced in 1931, which is also a long time ago. But after maybe experiments such as scattering in gas phase and from surfaces, people have realized that Ehrenfest method has problems. Initial problem that was identified is this branching problem because Ehrenfest method is a mean field approach in which you couple averages of quantum variables. And if you have a quantum wave packet, an atom that is quantum mechanical, that couples, scatters with the surface, and then it can scatter in two different ways. Scatter, for example, elastically or inelastically if some charge is transferred to the surface and there's some attraction force. Classical mechanics or Ehrenfest method would give you some trajectory that's going to be an average of the two outcomes that you would observe in an experiment, which is completely wrong if you try to simulate an experiment in which you have two separate outcomes. And this is because quantum mechanical wave packets can split, but classical trajectories cannot. This was something that gave origin of this technique called surface hopping, which is a very popular technique to model quantum dynamics in various systems. But later, when people started to model condensed phase systems, two more problems were identified with Ehrenfest, which for our applications are bigger problems than branching. The first one was equilibration. Turns out that if you couple classical particles to quantum particles using Ehrenfest, you can transfer energy from quantum to classical, but not from classical to quantum, but not from quantum to classical. And this was also realized by people that were studying conductance through molecules. When you would like to model inelastic scattering, when you send an electron through molecules and you have some energy loss to vibrations. So you don't have equilibrium at the long time limit because transfer of energy from quantum electrons to classical atoms is not described very well. And one other problem which we identified when I was a grad student was decoherence, because when you have a quantum system coupled to a quantum environment, which is large in condensed phase systems, you have many vibrations. If vibrations are quantum mechanical, your electrons lose coherence of any superposition of states that you can form when you make a transition. And this problem is not represented when you treat your vibrations classically. And this is very important when you want to study rates of transitions, because there's a thing called quantum Zeno effect, which is the limit of very fast decoherence. And decoherence is pretty fast in condensed phase systems. And this effect, it's a real effect. It says that transitions completely stop if you start measuring a system all the time. So if coherence is not maintained long enough, dynamics stops. And this effect is also missing. So we had to modify original Ehrenfest method to include those effects. And this was the first paper I published when I was independent, just finished PhD and became assistant professor. What we have done was to say, okay, let's consider quantum dynamics of an open system, in which case you have to add friction and noise, just like in classical mechanics, you have friction and noise that gives you classical Brownian motion. You can add those to quantum Chern-J equation, and then you have stochastic Chern-J equation. And these two terms, friction and noise, they describe basically all those effects. They describe branching because the property of those terms is to drive dynamics stochastically to eigenstates of this operator L, which is Lindblad operator, but its system environment, it's the interaction operator between electrons and vibrations. It drives the system to eigenstates of the operator stochastically, which gives you branching. Also it gives you decoherence because this is a system best type model. It also gives you detailed balance for a feature called velocity rescaling that I'll explain in a bit. But later we realized that doing dynamics in such cases is a little complicated because the potential energy surface that you have to run your classical dynamics on is changing all the time, and it's not very efficient. It's much more efficient to do these kinds of calculations when you stick to adiabatic potential energy surfaces that are easily available from various electronic structure calculations. And that's why we modified this initial methodology to develop a piecewise continuous version of stochastic Schrödinger equation and this mean field type description, which actually gave us surface hopping idea in which you can branch stochastically and you evolve deterministically for a while, but then at some point in time, there's a random hop that describes this kind of measurement process. So this is the methodology that we use most of the time in the group right now. I want to mention briefly that there are lots of different ways we can modify Ehrenfest. So last year we published a paper where we made it deterministic, which is the spirit of the initial Ehrenfest method, which makes it computationally efficient because you don't need to do stochastic sampling like you have to do with the surface hopping methodology. And there are a couple of papers that we based our methodology on. One is ours on decoherence, how to include detailed balance and decoherence deterministically into Ehrenfest method. Also, in the past, we worried about things like zero-point energy, which is important if you look at some processes that involve hydrogen atoms. So water splitting, for example, can be, you have isotope effects and zero-point energy can be important. So what we've done, we've modified Ehrenfest to add zero-point energy effects through moments of Q and P, and Q squared, P squared gives you extra terms that capture zero-point energy. And there are different ways to do this kind of extension of Ehrenfest. We developed a methodology called quantized Hamilton dynamics. And this is one simple version of it in which we made sure that the extra stuff that we calculate is very simple, such that this extra force that affects position momentum moments, second moments, is the same as you get in ordinary mean field. I'm just mentioning all this because probably most of the people in the audience, they have not been doing science in 2001, so these methodologies might be forgotten. And then there's another methodology we developed, which works quite well for high energy processes. There's a formulation of quantum mechanics based on Bohmian mechanics, in which you map a wave function into an ensemble of particles. So your electrons now form an ensemble of particles, and each particle evolves deterministically through a trajectory because you have to define a pretty complicated Bohmian potential that creates those fancy trajectories in the double slit experiment. And what we've done in this paper was to couple the classical particle not to an average like you do in Ehrenfest, but to make this trajectory, classical trajectory, capital X, dependent on the position of the quantum Bohmian particle. So now, instead of just one average trajectory, we have an ensemble of trajectories for the classical particles, each correlated with a different member of the Bohmian ensemble. How we compute decoherence time, which is important in the calculations. It's not a parameter. In the equations I showed you, for example, this equation, gamma, is just a parameter, but it's not a parameter in our calculations. We also compute it in an ab initio way. So there's nothing, no parameters at all in what we do. And we compute it using optical response theory, which has this pure dephasing time, which can be measured. So it's a very robust methodology, and it can be used by itself to compute something that's of interest to experimentalists, which gives you homogeneous line widths that can be measured for a single particle, or this pure dephasing time can be also measured in optical photon echo experiments. So the idea is that you have two states, and atoms move around, and when they fluctuate, the energy gap between two states also fluctuates because the surfaces are different. And you compute autocorrelation function of the energy gap fluctuation. And from this autocorrelation function, you compute this decoherence function, which is the pure dephasing time in the optical response theory. By fitting this function to Gaussian, because it looks very Gaussian, because it's time squared t is twice in the integral, double integral. By fitting to a Gaussian, we get the pure dephasing time, which is the decoherence time. And we had this very nice paper that Alexei Akimov, who's now faculty in Buffalo, wrote, where we did very simple analysis of this approach and derived this equation, which relates decoherence time to the fluctuation, the magnitude of the fluctuation. And this 1.02 is not a parameter, it's also derivable. It just happens to be this way. And we show that the decoherence time is short when a fluctuation is large. That's the main effect. Okay. And the last point of the methodology I'd like to discuss is the implementation in real-time TD-DFT. So we use DFT because that's a good way to describe electronic structure of the materials that we study. It combines efficiency and accuracy, and usually it works quite fine. So what we do, we solve time-dependent Conchem equations because you still need to use Conchem orbitals to represent DFT density. And when we solve the time-dependent Conchem equations, we solve them in a way that we can tie to many different standard codes. We use VASP mostly, also quantum espresso, tight binding DFT. So what we do, we take solutions of the time-dependent Conchem equations and use these adiabatic Conchem orbitals as the basis in which we expand the time-dependent Conchem equations. And when we do this, we end up with equations for the coefficients. And the coefficients follow this equation that contains the non-adiabatic coupling, which is the overlap type term and velocity. And this is something that we have to compute before we can start doing Ehrenfest or any other kinds of dynamics. So it has two parts, and it will come up in some of the applications. This first part tells you how sensitive wave functions are to nuclear motion, but it's also overlap type term. So if the two states don't overlap, it's 0. But also if they're not sensitive to a particular nuclear motion, it's 0. So there are two things in this matrix element. But it's multiplied also by nuclear velocity. So usually the faster the atoms move, so the higher the temperature, for example, the larger this matrix element. So this is electron-phonon coupling that we calculate in our applications, and this is what drives this is what drives electron dynamics, response of electrons to nuclear dynamics. I should say that when people implement Ehrenfest in real-time TD-DFT, they usually don't use this representation, adiabatic representation. They do it on a grid. But you can look at adiabatic basis as another representation to solve Ehrenfest methodology in real-time TD-DFT. It has advantages because the number of states is relatively small, because you can select those orbitals by energy, and then your basis can be fairly limited instead of using a huge grid. But you need to be able to calculate this non-adiabatic coupling in a good way. But this becomes critical, the representation, when you want to do surface hopping or include decoherence, detailed balance effects, because you have to define some states. And those states, there's a better way to do it. For example, you can use linear response TD-DFT states to define your excited states, but that's more expensive. So Conchem type representation gives us zeroth order adiabatic states, which give us very simple and efficient methodology, which captures many, many effects. So if you want to discuss many particle states, when you solve time-dependent Conchem equations, Conchem orbitals evolve in time, and you still make a Slater determinant of those Conchem orbitals to make sure that the density corresponds to some wave function. And if you now expand each orbital into adiabatic Conchem orbitals, then you expand this time-dependent Slater determinant into adiabatic Slater determinants, and then you have many-body wave function. And then we can include, recently we included Coulomb interactions explicitly that you can add to the Hamiltonian the way people do when they resolve time-dependent DFT in the linear response theory. But we don't solve linear response, we just use that an extra coupling in the Hamiltonian to solve the time-dependent problem. So you have this many electron bases, and then you can study problems that involve more than one particle, electron hole recombination, and so on. At some point, we studied multiple excitons and quantum dots, and you can see how big the basis grows. Even if you have just 25 valence band, 24 conduction band states, when you include double excitations, you already have 100,000 states, which is a huge basis. But there are some sparse matrix techniques that we've used in this case. There are reasons why Conchem representation works well in materials. but they're also discussed here. And this is the last approximation that we make, which makes it efficient. We call it classical path approximation. What we do, we pre-compute trajectory to drive electron dynamics. Usually it's the ground state trajectory, sometimes it's excited state trajectory. So this approximation does not really need to be done. We can also do full air and fast or surface hopping with trajectories following forces in the excited state. But this is a very efficient way to simplify. So this is the first simplification. We pre-compute the trajectory that drives electron dynamics, and dynamics of electrons is still highly non-equilibrium, but the trajectory is pre-computed. And the second approximation, we always use ground state density in the DFT functional. So when we compute Hamiltonian DFT functional, we can put a true density that evolves in time, that we evolve by solving time-dependent Kohn-Sham equations, but it's more efficient to just use ground state density all the time. So the justification is the following. First of all, we see in many applications that fluctuations of atoms, just due to thermal effects, are larger than differences in the geometries between ground and excited states. This is because we study materials that are pretty hard or that fluctuate a lot. And when you photoexcite, the excited force is not much different from the ground state force. And the second justification is that when you excite 1 or 2 electrons from hundreds of electrons that are present in a condensed matter system, the density does not change much. And why this is efficient? So instead of running multiple excited state trajectories, which is very expensive, we can run just one ground state trajectory. And we can update the DFT functional on the time scales of atoms, femtoseconds, instead of attoseconds on the time scales of electrons, because your electron density changes on attosecond time scale. And if you put it into the functional, it becomes, you have to update it quite often. Instead, we do it every femtosecond. So we've implemented all this methodology. Alexei Akimov, again, has done it in this code called Exciton. And most naturally, it's interfaced with Quantum Espresso, but we continue to use VASP in the group because that's what we've been using in the past. We also collaborated with Thomas Frauenheim and Shugara Pal, who's now faculty in India, has implemented this in tight binding DFT, DFTB, and also in games. And there's an overview article on the methodology that we published 4 years ago. And I'll stop for a second if there are any questions.
So yes, there is especially one question which refers to the basis sets which you're using for these calculations. So the question is, in fact, which basis sets do you recommend? I imagine that, I mean, the question if they are atom-centered versus not in these moving references can play a role. And also, once you have chosen the basis set, how many states do you typically need to include in the TD-DFT calculation?
Yes, so in the group, we mostly use VASP and we stick to VASP or DFTB, which is a purely plane wave basis set. But we have collaborations. There are codes, right, that use combination of atomic basis and plane waves, for example, or in games, we use atomic basis. Using this combination is more efficient. Personally, we don't have this implementation in the group, but we collaborate. Basically, whatever code is efficient electronic structure-wise, we are happy to use that code because the main expense actually is computing a normal DFT problem multiple times with high accuracy to get good wave functions to get non-adiabatic coupling. And in terms of applications, so we have to be careful about the size of the basis. Usually when we study electron transfer, electron hole recombination, charge trapping, then quantum dynamics is not computationally expensive, and we just select states by energy. Maybe we have 100 Kohn-Sham orbitals or something like that, maybe 1,000 states, and solving these equations in 1,000 state basis is not expensive. But if we want to study processes that involve 3 at least particles, or J-like processes, for example, or this is 4 particles, when we have double excited states, then things become very expensive. Then we have to do something. The easiest thing first is to select by energy, and then maybe use sparse matrix technique or something like that. But this is technology that Dr. Kim developed in the papers described below, so it's not available publicly.
Yeah, and then there's another question which just came now, which I just read it for you. The vibrations on the excited state, do you neglect them as well in this reflection scheme? Or is this not important because the temperature effects are dominating the system?
So in 90% of the calculations, we do ground state trajectories. So vibrations in the excited and ground states we assume are the same. But there are examples where excited state dynamics is important. So we studied water splitting and also proton transfer when you have methanol and TiO2. And in this case, we used excited state. So the simplest way to do excited state trajectory is to do delta SCF or some kind of constrained DFT where you constrain populations of excited state when you promote electron from HOMO to LUMO, for example, and constrain the population. And you can either do it self-consistently where you re-optimize DFT orbitals after you constrain populations, or you can use, you don't re-optimize, which is then you can do excited states beyond HOMO-LUMO, because if you start doing self-consistent iterations, once you constrain populations and you put electron into some orbital in conduction band, you can have convergence problems. But if you don't re-optimize orbitals, then you can do a calculation on an excited state. And this is how we do Ultrafast. So we compute orbitals in the ground state, don't re-optimize them, and we just constrain populations based on time-dependent Kohn-Sham equations.
Okay, so thank you for the moment. That's all.
Okay, so now I'm going to talk about some applications. First, I'll talk about quantum dots, which make a very nice story. And so the whole idea of quantum dots started back in the 1980s when people like Louis Bruce and Ekimov, they've considered what will happen to the properties of a semiconductor when you confine the semiconductor to a small volume. And at some point, size begins to matter. And basically what they've done, they solved the particle in the box problem for electrons and holes that you would get by considering solid state problem for particles in valence and conduction band. So you confine electron that has some effective mass in the conduction band to some spherical volume, and you solve the time-independent Schrödinger equation, particle in the box problem, and you get SPD-like states. And these states have gaps between them, and the smaller the particle, the larger the gaps. And you do the same for the hole. Usually holes in various semiconductors are heavier. That's why the splittings are smaller. And this is how you can predict that the color at which your quantum dot would emit would be size dependent. And in a way, this started the whole nanoscience field. When I came into this field in the early 2000s, the big topic was energy, and there was lots of effort to make efficient solar cells. So our first project actually was on Grätzel cells, but then we moved on to quantum dots. Why? Because there was a very interesting proposal from the NREL, Art Nozick, that said, oh, because now you have this kind of molecular type energy levels that have gaps, if you excite at higher energy, and when you absorb light, you absorb from infrared to ultraviolet, all this extra energy at the blue end of the sunlight spectrum is usually lost to heat because your band gap is tuned to somewhere towards the red. So what if you can use this extra energy for something more useful? And when you have gaps like this that open up, then you can expect that the energy is not going to be lost to heat very fast because there are going to be gaps that you have to cross. And because of that, you may be doing something useful. And there was this field of multiple excitons in quantum dots that then became also a singlet fission in molecular crystals and so on. So there was this very interesting prediction. And at that point, we realized that we're actually working at a very interesting interface of physics and chemistry. And we talked to chemists that make quantum dots, and then we talked to physicists that do the experiments. And there's actually a pretty big disconnect, not just in terms of different fields, but in terms of concepts and expectations, even methodology, right? You use phonons or you use vibrations. So when you have a quantum dot, is it a phonon or is it a vibration that you should use? But more importantly, conceptually, if you think of quantum dots as big molecules, then your expectation is very different from when you think of quantum dots as just small pieces of bulk. Because when you shine light on a molecule, you can dissociate a molecule. So electron-phonon interaction is very strong in molecules, but when you shine light on a piece of crystal, usually not much happens. Also, DFT, which is a band structure type calculation, usually works fine for crystals, but for molecules, that's why people develop many electronic structure methods based on wave functions. band structure calculation is too simple. So electron-hole correlation, electronic correlation effects are strong in molecules. Also, in molecules, structure is very important. If you isomerize or if you remove one atom, it's a whole different molecule, very different properties. But if you remove an atom from a piece of bulk, nothing changes really. But in this case, maybe size matters and shape. And molecules have discrete energy levels, but bulk materials have bands. But going back to what we wanted to study is we want to study cooling, and we wanted to see if this idea that cooling will be slow when you make a crystal into a quantum dot, so that energy gaps open up, if it will be slow, and then if it will be slow, can you make multiple excitons when you have this extra energy that you take and you use it to create more charges. So the extra energy, instead of going to heat, is used to excite a second electron. So this all started in 2004 when Viktor Klimov published PRL, which showed quantum yield, which is how many electron hole pairs you excite per one photon. And if the photon energy became bigger than 2 band gaps, or better 3 band gaps, you start seeing more than 100% yield, meaning that you excite more than 1 electron hole pair. And then in a couple of months, this nano letter came out where people measured the time scale for this process, which was very fast, less than a picosecond. But then surprises came along. First of all, Viktor Klimov also measured relaxation times, electron phonon relaxation times, and they found relaxation to be very fast. So this idea that you can have a phonon bottleneck, that your relaxation will be slow because you have gaps in the energy spectrum of quantum dots, predicted that this should be nanoseconds, but in fact, it was sub-picosecond as well. So why? And second, even more interesting question, the size dependence. Particle in the box model predicted that when you make your quantum dot smaller, the gaps open up and you should have slower relaxation, but in the measurements, the relaxation was faster, though not slower. So no bottleneck, and relaxation becomes faster for smaller dots, totally opposite from what you predict from this very simple particle in the box model that works very well for spectroscopy. And this is what predicted size dependent luminescence, for example. So then people like Munji Bhavendi started to reproduce the data, and they became quite critical. They predicted, there's actually no effect. So, and it takes quite a lot of effort to publish something that's negative. So people questioned the initial experiments. There's no multiple exciton generation. So what happened is that you really have to be more realistic about the quantum dots. So quantum dots are not perfect. They blink. There are all sorts of things that can happen. And in the interpretation, so the data was fine, but when you interpret the data, you have to include other phenomena into consideration. So for example, in this review, Viktor Klimov pointed out that if you make your measurements 2 different ways, if you stir your sample, if you keep supplying new quantum dots, then you have one signal, but if you shine light on the same quantum dot all the time, then you have a different signal. So presumably when you shine light on the quantum dot, you damage it photochemically. They become dark or they blink or something happens. Basically, you introduce defects. And those defects introduce new processes. So this is something that you have to understand already at the atomistic level, because this very simple picture of the quantum dot, that's just a particle in the box, is too simplistic in this case. So what happened to the multiple exciton field is that the analysis was redone, and then the estimates of the efficiency were reduced. There were still examples that gave you 200% efficient or so, but most interpretations converged on efficiencies that are maybe 150% or so. So then there was this paper by Philippe Guillot-Sionnet in Science that finally found the bottleneck. So he found a relaxation time, electron phonon relaxation time from P to S state of electron to be on the nanosecond. But he had to separate electron from the hole. So he created this very complicated structure in which he put some trap on the surface, hole trap. And first he removed the hole as one step, and then he was doing dynamics of electron in the absence of the hole. And when the hole was far enough, when this shell was thick enough, he would see relaxation time from P to S to go into nanoseconds from picoseconds. But this is something very special. Still, the question remained, how come in general relaxation is very fast? So there are basically 2 big questions that we try to address. Why is relaxation fast? And second, how can you still make multiple excitons with 150% yield, even if relaxation is fast. So the first calculations that we've done showed us that this very simple model, particle in the box model, kind of works, but it's too simplistic. So if you look at states that you get from optimistic calculation, you see that, yes, you can call SPD type states and you can see PX, PY, PD symmetries maybe, but this is all garbled because this is not a sphere. You have a surface states, you have relaxation, you have thermal fluctuations, and if you look at the bigger dot, it's impossible to assign those states to any kind of symmetry, P-like or S-type symmetry. But the main conclusion, which actually was known to people because this picture on the right is taken from a review article from 1999, is that really you don't have gaps in the spectra of quantum dots. If you stop and think for a second, when you have a particle quantum dot that has 100 atoms, in each atom contributes maybe 4 states into valence and conduction band, you have 1,000 times 1,000, you have 400 times 400 states, basically, single excitation. So you have thousands of excitations within the energy range of a few EVs. So you don't have gaps in the spectrum. You still have these peaks that make it look atom-like, and those peaks is something that particle in the box model predicts very well, because you have envelope functions that are SPD, but under each envelope function, you have many, many excitations. And because the spectrum is so dense, you don't have a relaxation bottleneck. It goes very fast. There are some special cases at very low energy. Yes, you have gaps, and then you can have this bottleneck. But at high energies, the density of states is very high. And that's why when you try to make multiple excitons, when you excite it twice the gap, then there's no bottleneck. In this particular material that Philip Gyotze studied in cadmium selenide, for some reason, there is one state that's split from the conduction band. So you have this gap for any size quantum dot that we studied, and that's why you have this bottleneck. And the reason why we have this bottleneck in the calculation, because it's a multi-phonon process, because the gap is a few tens of EV, and these are all heavy materials, right? So the frequencies are very slow. So you have to excite multiple phonons to accommodate this electronic energy when you go from P to S state, and that's why this is a slow process. And we had to include this decoherence fact to be able to predict it. So then the question is, how can you create multiple excitons? This is not an easy question, because initially there was this traditional mechanism called inverse Auger or impact ionization that comes from bulk semiconductor physics that tells you, oh, you have electron and hole, and then they move. And if they have extra energy and they collide, you can have a scattering event that creates a superposition. Oh, you have a scattering event that creates a second electron hole pair. However, this requires some time, and this is not very efficient. So we considered another mechanism that came more from chemistry that considered the possibility that you can excite states that are already superpositions of single and double excitons. We did, so the physics actually is also quite simple in all cases. When you consider density of states of singly and double excited states, there's some kind of crossover. And this crossover happens at maybe 3 times the gaps. So if the gap is 2 EV, it happens around 6 EV, or maybe 2.8 times the gap. And this is quite universal in all materials. So at high energy, you have many more double excitons than single excitons. At low energies, you don't have double excitons. So when you photoexcite at high energy and double and single excitons are coupled in some way, then statistically, if you excite a single exciton that's optically active, the population will go to double excitons. But as you drop in energy, and if you drop below this threshold, then you see a double exciton annihilation, because now there are many more single excitons than double excitons, and then all the population goes into single exciton. So if you photoexcite at 3 times the gap, you can see double excitons, whatever mechanism you consider. If you excite less than 3 times the gap, then you're not going to see many double excitons. And we saw this process, this impact ionization type mechanism, where you start in single exciton and then single excitons become double, so this density disappears, and then you recover single excitons at the energies below this crossover. But then we also considered more advanced calculations that involved electronic structure methodology, where we said, oh, when your quantum dot is small enough, it's really like a molecule, And when it's a molecule, you don't excite singles or doubles, you excite superpositions. So you can have a double exciton type state that has maybe 5 or 10% of single exciton character. This explains why it can have some optical intensity, because simple optical selection rules does not allow excitation of double excitons, only single excitons. But if there's a mixture superposition, then double exciton can attain some optical intensity. And we've done these extensive calculations, configuration, interaction, chemistry style calculations on small quantum dots, on 12 atom quantum dots. And we see also if the gap is about 3, so 3 times 2.5 or so, you have this threshold at which you see transition to double excited states. And it happens that in lead selenide, because of the symmetry of the band structure, all states that you excite are 95% double excited states. And that's why this was the material where multiple excitons were discovered first. But in other materials, you also have this transition, but then you can excite various superpositions of single and double excited states. And the intensity drops because double excited states are not optically active, but it's not zero because they are mixtures with single excited states. And then we could explain why you have different experimental results depending on how good your quantum dots are. Because when you have some defect state, you have a mid-gap trap state, your double exciton, double excited state can be created when you photoexcite one electron across the gap, but another electron from this defect state into the band. But this is not the double exciton that you need, right? Because you need to create electron and hole. But in this case, your hole remains in the trap state that was filled initially, and this is not the hole that can be used to conduct electricity and make a solar cell. And so then we did some extensive calculations and showed that at the energies when before we had very nice double excitons, now we have this transition that involves intraband transition in a single exciton, and this is not what you need. And that's why the efficiency drops if your quantum dot is not perfect. I should probably skip some slides. I want to mention briefly, Auger processes are very common. Right, and this is something that we realized once we started to look at quantum dots in other systems, because these are, so you have particles that are confined, but you still have high densities of states. So when you look at molecules, in molecules you have very strong electron-hole interactions, and when you do singlet fission in a molecular crystal, when you excite 2 electrons, lots of things can happen, and the electronic structure is completely different, because you have to redo the calculation for double excited state. It's not just twice single excited state and so on. In quantum dots, it's a little simpler. Double excited states are pretty much twice single excited states, but still interaction between electrons and holes is strong. But in addition, in comparison to molecules, quantum dots and other nanoscale materials have high densities of states. And when you have Auger-like process, you have to have 2 conditions. You have to have interaction between particles, and you have to have many final states into which you can scatter. And this is what's maintained in quantum dots and other nanoscale materials that's not maintained in molecules or in bulk. In bulk, you don't have strong interaction between particles. In molecules, you don't have many states. So therefore, Auger-like processes should be very, very common in nanoscale confined materials. And this is one example where in chemistry, we use this Marcus theory, which is very popular. It was predicted in the 1950s that if you look at electron transfer from some donor state to acceptor state, and you increase the energy gap from donor to acceptor, in this case, you have quantum dot, you photoexcite the quantum dot, and then from this the excited state of the quantum dot, you transfer electron to a molecule. And this theory predicts that if the energy gap becomes larger and larger, initially the rate goes up, but then it goes down. And this was a very simple model. The reason why the rate goes down, because you have this transition state over which you have to go. So if you have initial state here, and then there's a maximum that you have to overcome, when your final state drops, the maximum becomes lower because the 2 parabolas cross at a lower energy. But eventually you start to see this crossing on the opposite end, which was known as Marcus inverted regime. And that's why you now have a barrier on the opposite end, and you have this drop in the rate. So this was a very simple model, very unusual prediction, because normal intuition tells you the bigger the driving force, the faster the reaction. But no, if the force is too big, the difference is too large, then the reaction slows down. So Tim Lian measured this in quantum dots with the molecule, and he tuned quantum dot size, he tuned the molecule, to cover this whole range. And instead of turnover, he saw this saturation. And we basically explained it in the calculation. We showed that this is because you have Auger-like process. When the electron drops, you also excite the hole. And Marcus theory, simple Marcus theory, does not include this into consideration. It assumes that energy goes to vibrations. But in this case, your final state involves hole excitation, but this hole excitation is very, very brief. So if you look at our dynamics data, you have for the excitation of the hole that starts right away, but after 3 picoseconds, the hole relaxed all the way back to the edge of the valence band because the density of states is high, and therefore there is no hole excited, and actually it's very hard to detect because this happens very fast. But it totally changes the behavior. So if you allow hole excitation, then you have the saturation, but if you don't allow hole excitation, you have normal turnover as in standard Marcus theory. And last thing about quantum dots is now it's metallic, so it's not really a semiconducting quantum dot, but it's also a very important hot field. When it took us 10 years to start working on metallic particles because people still question how well can you do in describing plasmon-like excitations if your size of the particle is very small. So it's not a true plasmon, but lots of people, such as George Schatz, they've shown that you can do atomistic calculation, and if you increase particle size, eventually you get plasmon-like excitations. So this was a model, but the question was very interesting to the whole plasmonics field, which is how can you do something useful if you have a metallic particle and electrons and holes that you generate are going to recombine very fast, right? If you have a metallic particle, everything decays to heat very, very fast. So there was a traditional mechanism of plasmon-driven electron transfer when you excite a plasmon-like state at the peak of your pyramid. And then, so because it has highest density at the sharp points of your particle. And then, according to this mechanism, this collective excitation of electrons and holes dephases or decoheres very fast into free particles on 10 femtosecond time scale, and then electron injects. But how can it inject? Why doesn't it recombine with the hole if this material is metallic? So we've done some calculations on this, and we've seen states like that where you have plasmon-like excitation, which has the right energy, has the right density, but it has a pretty substantial tail that extends into the TiO2 in this case. And we said, in this paper, actually there's a maybe 20% probability that your electron is already delocalized into the acceptor. So you photoexcite this kind of state that already has partial electron transfer character. And this was 2014. And then 2015, Tim Lian publishes this paper where he basically shows this experimentally. What he's done in this work, he's studied energy dependence of the yield of injection. So he photoexcites plasmon-like states or plasmons. And he sees that there is a sharp threshold. So normal models that follow traditional mechanism tell you there should be continuous energy dependence, because when you generate electron hole pairs, the larger the gap between electron and hole, the more likely your electron will be high enough in energy to inject into the conduction band. But instead of this gradual increase in the efficiency, he saw this sharp onset. And this is because you photoexcite a state that is already with electron already delocalized into the acceptor. And this is what we predicted 1 year ago. And then more recently, we studied what happens when you put this on a 2D material, and we actually saw substantial differences, because when you have a 3D material like gold on TiO2, or in Tim's experiment was gold grown on cadmium selenide, you don't have, your interface is basically chemically bound. You create chemical bonds. But when you put it on 2D material, because 2D material is happy by itself, the chemical interaction across the interface is much weaker. And therefore, this mechanism in which you photoexcite a state that's already delocalized onto the acceptor, it works to much lesser extent. As you can compare, this density extends much less than this density. So this is the end of quantum dots, and maybe you have questions about that. I've seen some chat messages.
Yeah, sure. There are some questions, obviously. So one is linked to the multi-exciton generation. The question is, does this exist only in quantum dots or also in bulk materials? And linked to that, can you say something about the relaxation and the time scales of the relaxation?
Yes, so in bulk semiconductor literature, this is known for a long time, and it's called impact ionization. The efficiency is low, a few percent, and that's why people don't really worry about it too much. Although I think it becomes important if your current becomes strong, so you have extra scattering, charge scattering events that become important when carrier density is high. So I think the whole physics is pretty much similar in terms of relaxation. You have high densities of states, so electron vibrational relaxation and electron scattering. Yeah, the scattering depends on how close your particles are, obviously, on the volume or charge carrier density. But electron phonon relaxation is similar in bulk materials and in quantum dots. Efficiency is much higher in quantum dots because particles are close to each other and the interaction is much stronger, and the scattering is also much stronger. Yeah.
Okay. And then another question is about the use of TD-DFT, which you have. Can you say something if one could use some post-Hartree Fock methods or something?
Yeah, so when we studied multiple extons, we used configuration interaction. This was not time dependent. So this data that I show you, all these calculations were done configuration interaction type methodology. But this is very expensive. That's why we could do only 12 atom systems. These are real quantum dots, if you can call them. Yeah, so what we do can be done with with other methodologies, not necessarily DFT, but it's just complicated and expensive. And we usually focus on systems where DFT or DFT with Coulomb interaction between electron and hole can give reasonable description. And there are lots of materials, including perovskites, for example, where DFT is quite fine. Yeah.
Mm-hmm. And then one final point is, can you explain the kind of, if there are similar physics behind the double excitations and singlet fission, and can you say something about the link between these things?
Right. So it's the same type of process where you excite one electron hole pair, which is a singlet excitation, and then in singlet fission you create two triplets. So it's the same as when you created two excitons in a quantum dot. But the electronic structure is quite different. So in the case of multiple excitons in quantum dots, you have to excite at least at twice the gap, because your double excited state is twice the energy of the single excited state. But in the molecular crystals, your triplet state is half the energy, or at least you can make such materials where your triplet state is half the energy of the singlet. So you can excite at the lowest singlet, not at twice the gap, at the lowest singlet, and still get singlet fission. So I think the physics is more or less the same. You can also create superpositions. People discuss a lot the mechanism, and there are some dark states or intermediate states, and you can photoexcite superposition of single and double, singlet and triplet pair in a singlet fission, or it can be a stepwise process, but the energy levels are quite different. So the electronic structure, your DFT cannot do this. Even linear response to DFT may not be quite suitable for double excitations, for example.
Yeah, sure. Okay, so I think we should continue. There are some more questions which we can address perhaps in the end.
Yeah, so I don't have too much time. Should I have 5 minutes or?
Yeah, sure. Mm-hmm.
Yeah, so probably I'll skip 4. Perovskites, very interesting topic. This is another example where it's neither chemistry nor physics. So it's some material that is somewhere between solid state, like silicon or cadmium selenide, but also has some features of organic. So it's quite soft. So what is perovskite? You have inorganic lattice, but then there's enough space in between such that you create, you have cavities that are filled either with small organic molecules or with large inorganic cations. And this molecule that's inside can move quite a lot. It can rotate. It's hindered rotation, but still rotation. And the overall structure is rigid enough so that it can conduct electricity quite well. But at the same time, it has features almost like a liquid, because when your molecule rotates, its dipole moment moves, and you can talk about salvation effects and so on. So it's a very interesting material. Why it's so popular? Because for some reason, the efficiency when you make solar cells or some detectors or something is very high. While in traditional solar cells, silicon technology had to be developed to eliminate defects. But defects in metal halide perovskites are not so bad. So the question is why? So we've worked quite a lot on this in the last 4 years, maybe or so. So the key points. So defects are benign because really they decouple from conduction valence bands. So in this case, we looked at interstitial extra atom that exists. So suppose in this cavity, in addition to the molecule, you have an extra iodine, which can happen a lot, and it creates a mid-gap trap state. So this trap state is inside the gap, but it's not so deep inside the gap. That's actually another reason that the trap states are not very deep. But from our point of view, what's really interesting is that this state is really decoupled from the bands because the spacing between the atoms in the inorganic lattice is large, so that when you have this trap state in the middle, it's overlapped with the states in this case, it's important how it overlaps with the conduction band state because it's a whole trap state is very small. So the non-adiabatic coupling is small. And what we see is that if electron-hole recombination without defect takes in this model 100 nanoseconds, when you have trapping is fast, but the recombination of trapped hole with electron is slower than free hole and free electron. So in fact, there's enough time for this trapped hole to go back out. And that's why in this case, you can even say that a trap state increases lifetime because instead of recombining, it lives here for a while and then it goes back the hole and conducts. So in this case, defect does not reduce efficiency. So then we also looked at vacancy. So instead of extra iodine, it's missing iodine. And what's really interesting here is that there's a very strong dependence on the excitation state. So if you excite quantum dot that I just discussed, and you create 1, 2, 3, 4 charges there, the electronic structure and the properties don't change much. So you have the same material, the structure is the same, the energy levels are more or less the same. But if you put extra charge or 2 charges into perovskite that has a defect, the whole thing changes. You can even make new bonds. You can create a lead dimer. The mid-gap states appear, new states appear, and so on. So we see very strong dependence of lifetime on the oxidation state of this vacancy, which should be very relevant because when you start sending currents through perovskites, you should see very big drop in the efficiency because when you have your vacancy in normal state, then it doesn't really create any deep trap states. But when you start oxidizing, then you create lots of new trap states, and then relaxation becomes very fast. So another interesting effect about what passivation does. So normally you assume, okay, you have a trap state, and this trap state is removed when you passivate it. But first of all, this trap state is not really deep, right? And it does not, by itself, it does not do much. Still, it lowers down the lifetime, but not by much. But what we see in the calculation is that passivation does not really eliminate the trap state, or that's not the main effect. The main effect is that you separate electron and hole. So in this case, we also have iodine vacancy on the surface. And when we have this vacancy, both electron and hole become localized near the vacancy, and that's why relaxation becomes faster. But when you passivate, and this works with lots of different molecules, in this example, it's just oxygen from atmosphere, but you can have a loose base molecule, or even water can do it. When you put it in this vacancy, it separates electron from hole. So electron remains localized around this, but the hole becomes localized away from the defect. And when you separate the electron and hole, you reduce the non-adiabatic coupling and your lifetime becomes longer. So it's a different passivation mechanism. You don't remove the state, but you separate electrons and holes. So interesting effects. So people play a lot with composition, and the best perovskites perform well because they were tuned to make very complicated composition. So this was just one paper where we studied why when you put bromines, lifetime is shorter than when you have iodines. It's very simple. Bromines are faster. Electron-hole coupling is stronger. But then there was an interesting phenomenon when they replaced Ma, this molecule inside, with a bigger molecule. And this molecule inside apparently should not have any effect on the lifetime because it does not contribute to electron and hole wave functions. So it's just something that stays there, but should not contribute to the properties of electrons and holes, but it does. And it shows this interplay. What happens when you have a bigger molecule, you reduce the atomic motions. And when you reduce the atomic motions, electron-hole coupling reduces because you have stiffer lattice. So when the lattice becomes stiffer, then the dynamics slows down. So then there was an interesting also phenomenon, temperature dependence. Normally, if you increase temperature, the lifetime goes down. But in experiments, people see efficiency and lifetime actually goes up with temperature, which is strange. If you look at the non-adiabatic coupling, you see this velocity, and velocity increases with temperature. So the coupling should be larger when you increase temperature, but it comes out to be smaller. Why? Because of disorder. So what happens if you increase temperature, the structure fluctuates more. And when the structure fluctuates more, electrons and holes don't overlap as much. So you create small amount of disorder. You still maintain bands. So the states are still delocalized, but there's still some localization already at room temperature. And this localization decreases overlap of electrons and holes. And this matrix element goes down. And that's why non-adiabatic coupling goes down and lifetime goes up, which is something that is opposite from what you see in normal inorganic semiconductors. So recently, machine learning is a popular field, so it's hard to stay away from that. And we have, I have every second student in my group take machine learning classes, so I figure out better, we start doing something. So we analyzed what causes non-adiabatic coupling and relaxation. And so we did something quite simple, but the conclusion is quite interesting. First of all, just as I pointed out here, this matrix element geometry that defines localization of wave function becomes more important than motions. So that's the first thing that we see. Geometry is more important than motion. So the correlation is more with structural features than velocities, than with motions. So then we also identified an angle. People usually talk about this angle, but we identified some other angle that's actually even more important. And finally, we also see that motions and even configuration of MA, of this organic part that's inside, is also important. It's not negligible. It's not the most important feature, but it's still quite important. Yeah, maybe last topic, and I should stop. There's lots of synergy, right? So this material is very interesting because many things can happen. In particular, those vacancies or interstitials defects can migrate. And what we studied, what can happen to the relaxation when atom migrates. In this case, vacancy migrates. So what we see is that the vacancy does not really create any deep trap states. And in this material, in fact, it has no trap state. But when it migrates, the whole thing changes. So even though normal ground state optimized geometry calculation says, oh, there's no trap state, but if you start doing dynamics and on some time scale, you see migration of this defect, everything changes. You have this mid-gap state that shows up when the defect migrates. And because of the mid-gap state, the acceleration of we have a 10-fold acceleration in the relaxation time. And this persists for a while, even though defect already migrated to a new part, it takes some time for the structure to relax. So for a while, even after migration, this mid-gap state persists and relaxation is quite fast. I think I should stop probably, right, Ralph, because of time constraints.
Yeah, I think time is over more or less. So yeah,
so I think I'll stop if there's any more questions right now or tomorrow.
Okay, so thank you very much, Oleg, for your contribution. So I'm clapping in the name of everyone else who we cannot hear. So there are some questions still open. One refers to the previous part of your talk, where you have shown the gold on top of the molybdenum disulfide substrate. Okay, and the question is, how is the plasmon of the gold cluster affected by the substrate?
So when we put it on a 2D material, does not extend into 2D material as much as when we put it on a 3D material. When we put a surface on a surface with unsaturated chemical bonds, we have this delocalization. So it's the same particle, but on TiO2, and this yellow density extends a lot, but here it extends much less. And if the interface is even smaller, this is now a cylinder, not pyramid, basically there's very little extension. So that's the main difference. The chemical interaction across the interface, there's no chemical interaction, and that's why the interaction is weaker. Yeah. Okay.
And then there's another question also relating to the phonon bottleneck, which you have been explaining. The question is, how can you relate that bottleneck with the quantum dot states? Or can one, or how can you?
Yeah, so there's no real bottleneck. So first of all, there are no big gaps between states, usually. There are some cases in which there are gaps between states. And this is for the first two states of electron. But even in this case, you sometimes don't see bottleneck because you have this hole and you have this Auger-like process where when the electron goes down in energy, it gives energy to the hole. So people need to remove this process as well. So that's why when Philippe Giotsene did this experiment, he had to remove the hole before he could see the bottleneck from P to S state. Otherwise, you have this Auger-like process that kills the bottleneck. So basically, there's no bottleneck, and the gaps between states are really small, except for very special conditions that you can create, but it's not general. Yeah.
Okay, very good. Now, one last question. I just read it to you. How is the exciton splitting taking place in a donor-acceptor organic system where there is a van der Waals interaction which is predominant? And how do you optimize the spatial distance between donor and acceptor?
So we just turn on van der Waals correction into DFT, right? How exciton splitting? So it's
one of these D2 or D3 corrections, you mean? One of those?
Yeah, D3 usually. Yeah, right. One of those, exactly. Exciton splitting. So organics really, DFT, I mean, so again, quick question, answer, we don't really study organics much. We had a couple of papers on singlet fission, but we had to adjust. So DFT was not doing well at all. So we had to do some other calculations and build a model. So organics are more complicated. You have to do more than just band structure DFT that we do. And that's why we don't really do organics much. So there are other people that do organics in a better way. Yeah. Because exciton splitting, all that is important. Yeah.
Okay, so that was all for now. And thank you very much again, Oleg, for this very nice talk. And I remind everyone that tomorrow we will have a question and answer session where you can ask further questions to Oleg and also to the next speaker. Okay, so thank you very much again. I clap for everyone. So I give again the chair of chairman, the role of chairman to Nicola Seriani, who will chair the next talk and introduce the speaker. Okay.
Thank you. And I passed directly to introduce the next speaker, who is Marco Bernardi for the California Institute of Technology. So thank you. The stage is yours. I think we can start straight away. Thank you.
Okay, well, thank you very much. Let me briefly set up. Okay, so first of all, I would like to thank the organizers for inviting me. It is a pleasure to give this talk, and I'd like to thank all of you for attending this virtual seminar. So in the next 45 minutes, I would like to tell you about the work that we do at Caltech on modeling ultrafast dynamics of coupled electrons, phonons, and excitons using first principles calculations. Now, so-called pump probe ultrafast spectroscopies have truly opened a window on the dynamics of materials out of equilibrium. These techniques are able to probe very short timescales that are characteristic of the motion of electrons and atomic nuclei in materials. For example, using short optical or X-ray pulses, people are able to excite electrons and then probe their dynamics with a near femtosecond time resolution. At longer time scales, as the electrons give out the energy to the lattice vibrations, so-called phonons, there's a range of time domain diffraction techniques, typically employing electrons or X-rays that are able to probe the structural dynamics and the specific lattice vibrations contributing to it. These processes tend to occur on longer time scales of picoseconds or longer. Now, these experiments are done both in tabletop setups and also at large-scale facilities, such as free electron lasers, for example. They're fascinating because they can probe the interactions inside materials and even manipulate matter for short transients. However, the results of these experiments are difficult to interpret. So this is an area where there is a critical need for accurate theory to both predict and help interpret the result of these complex experiments. For this reason, with my group, we investigate the dynamics of materials out of equilibrium using so-called first principles calculations, which, as you know, take the structure of the materials, the only input, and use quantum mechanics to solve for the relevant properties of interest. And the goal with these techniques is to truly achieve quantitative accuracy without using any free parameters, for example. So one goal of these calculations is to fully reconstruct the cascade that occurs in a material after you excite it. So the excited electrons that evolve on femtosecond timescales, then the structural dynamics due to phonons on longer picosecond timescales, and ultimately the carrier recombination. Another goal is to go beyond what experiments are capable of and truly shed light on the microscopic mechanisms governing these processes. A key piece of physics in this context is the interaction between the electrons and the lattice vibrations, or phonons, and the ability to accurately compute these electron-phonon interactions using first principle techniques based on density functional theory will in fact be instrumental to what I will say next. So let me briefly review the main ideas now. As you know, the atomic nuclei in materials vibrate due to their thermal motion, and they perturb the potential seen by the electrons in a crystal, for example. This perturbation is shown here in red. And so to lowest order, one can formulate the interaction between the electrons and lattice vibrations with this Hamiltonian, which is the lowest order theory. So it works for weak electron-phonon coupling that is typical of many metals and semiconductors. Now, within this level of theory, the effect of the lattice vibrations is to scatter an electron from an initial state with a given band and K point into a different final electronic state by emitting or absorbing a phonon with a certain wave vector Q and branch index nu. So this could be an acoustic or optical phonon. It could be longitudinal or transverse. The key quantity that we're interested in first principles calculations is the probability amplitude for each of these processes. And this is the so-called electron-phonon coupling matrix element. This is challenging to access with simplified analytical models because you need the wave functions of both the initial and final states and the change in potential due to each specific vibrational mode. However, using first principles calculations based on density functional theory, we can fully compute these matrix elements in the entire Brillouin zone and then use them to model the ultrafast dynamics. This workflow that I'm showing here has become better established over the last 5 years, and I would like to briefly summarize it. So the first ingredient is you can get the band structure and wave functions from density functional theory, and then with its linear response extension, the so-called density functional perturbation theory, or DFPT, you can obtain the phonon dispersions and change in potential. And so now you have all the ingredients to form the electron-phonon interactions. One challenge, however, is that because density functional perturbation theory is a rather costly method, you can typically do these calculations only on relatively coarse Brillouin zone grids, so something like 10 by 10 by 10 points, for example. The challenge, however, is that to fully capture the excited electron dynamics, you typically need significantly finer grids of order 100 by 100 by 100, for example, because you want to capture scattering processes in fine features of the Brillouin zone, for example, intra-valley and inter-valley processes. So the key technology here is to transform these matrix elements to a localized basis representation where the electron-phonon coupling now looks like the scattering between two localized orbitals due to a perturbation at a third site. And for most phonon modes, for example, nearly always for all acoustic modes, this interaction is short-ranged, therefore it decays rapidly in real space. Once you compute it on moderate grids in this localized basis, then you can do double Fourier transform and interpolate the interactions to arbitrarily fine grids in the Brillouin zones. And typically you end up using millions or billions of these matrix elements. And then you can compute, for example, electrical transport properties, which is one of the focuses of my group that I will not discuss today, or ultrafast dynamics, which is the topic of this talk. Now, the first half of the calculations, the density functional theory, you can do with a standard DFT code like quantum espresso. However, forming the matrix elements and manipulating them and using them to carry out dynamics needs more specialized codes and workflows. This is the reason why, starting 5 years ago with my group at Caltech, we started developing Perturbo, which is an open source code to carry out these processes of forming matrix elements and studying dynamics with high efficiency. The code has been released early this year. It already has over 150 users, and we'll actually have workshops in the fall to train new users for those of you who may be interested. Now, this strategy is also common to other interactions that I will use in this talk, for example, phonon-phonon or Exciton-phonon, where there is an external code where you compute some perturbation quantities, and then we farm the matrix elements and use them within our code. Now, once you have this machinery in place, the question is, what new science can you do? So I'll show you perhaps the simplest possible calculation you can do, which is computing the electron-phonon scattering rates. This is the rate at which an electron gets scattered out of an electronic state. And in lowest order theory, so for weak electron-phonon coupling, it basically takes the Fermi's golden rules form. So you have a Brillouin zone integral of the square of the matrix elements, and then you have a process for phonon emission and a process for phonon absorption. The inverse of these scattering rates are the relaxation times that essentially give you an idea for the time scale for energy loss for excited electrons. And so it is a first step toward the dynamics, not a full actual first principles dynamics, but you can use it, for example, to attempt to interpret some experiments. When I started this work as a postdoc in 2014, at the time it was actually hard enough to converge these relaxation times due to this Brillouin zone integral, which is very slowly converging. So at the time we're storing terabytes of data for even simple calculations on a material like silicon. So what we were able to show at the time for silicon is we fully converged the relaxation times due to electron-phonon processes. We've shown that near the band edges, they tend to be longer. These are relaxation times at room temperature due to the smaller density of states. However, as you go deeper into the bands, the relaxation times get shorter because you have a higher density of states. But there's also a non-trivial dependence of the matrix elements on momentum, and holes and electrons tend to scatter at different rates. Equipped with these relaxation times, the simplest thing you can do is you can do a highly approximate solution of the Boltzmann equation, where you say, okay, at time 0, I simulate an excitation in the material, and then I time step it to equilibrium within the relaxation time approximation. So each state goes to equilibrium with its own relaxation time computed from first principles. So at the time, we're interested in carriers excited by sunlight in silicon. So we modeled the process of what happens to excited or so-called hot electrons in silicon. You see, if you simulate a pulse of sunlight, it essentially creates carriers in the conduction band that extend for a couple of electron volts above the conduction band minimum. And over a short time, they will relax to the equilibrium Fermi-Dirac distribution. You run the calculation, and so you find out that the typical time it takes for the population to relax is of order 250 femtoseconds, which is consistent with transient absorption experiments. So that was the starting point for us to use these tools, so calculations of relaxation times and inelastic mean free paths, to investigate a range of semiconductors and metals. And you can predict relevant timescales, interpret experiments, but obviously there was still a need at the time for an actual tool to perform real-time dynamics using the Boltzmann equation. That tool I started developing at Caltech in 2015, and we first showed the full solution of the Boltzmann transport equation for carriers in 2017. More recently, we've been able to study the coupled dynamics of electrons and phonons, and more recently also excitons. And so this will be the topic that I'd like to discuss in the remainder of my talk. Before I start telling you about how we implemented the Boltzmann transport equation, I'd like to take a step back and compare to various existing methods to investigate non-equilibrium dynamics. Loosely speaking, you'd like to investigate the motion of electrons and atoms in materials. So there's a variety of approaches to do that. A widely popular one, as we saw in the previous talk, is time-dependent density functional theory, which has been widely used and widely successful for molecules. It can give you, by solving the time-dependent Kohn-Sham-Schrödinger-like equation, the electron density and atomic positions as a function of time through Ehrenfest forces, for example. Despite its wide success, there are some limitations to time-dependent density functional theory. One of them, for example, is that the interactions are approximate, and they're essentially the approximation is contained in the treatment of the exchange correlation functional. And it is not trivial how they affect the dynamics. For example, how they affect the interactions between the electrons and nuclei, and how you would even validate that you use the correct interactions. The other one is that because it's a fully quantum dynamics, it's typically limited to shorter time scales. So you need very short time steps. And so it's limited to time scales of typically less than a picosecond in most calculations. Now, by contrast, the Boltzmann transport equation dynamics that I will discuss today is a semi-classical approach to evolve the populations, in this case of electrons and phonons. The novelty here is that you can compute the collision processes entirely from first principles. Two advantages are that you can use interactions that you know to be accurate, and you can actually validate and you put them in by hand, essentially. And the second one, as I will show in this talk, is that you can go to up to very long time scales that are characteristic of the structural dynamics, while also retaining accuracy on the femtosecond time scale of relevance for the electron dynamics. Now, in the bigger picture of available methods, you can regard the Boltzmann transport equation as the lowest rung of a ladder of methods, where the highest, most accurate, but extremely computationally expensive are the non-equilibrium Green's functions. And then if you compute them only in one time, you basically fall back into the Liouville equation that time steps the density matrix. So that involves also the coherences. However, the coherences tend to be short-lived, let's say sub 10 femtoseconds. So if you are only interested in the regime that follows, for example, the first couple of tens of femtoseconds after the excitation pulse, then you can focus just on the populations, and that's where the Boltzmann equation can be applied and can also give very valuable information. So how do we solve the Boltzmann transport equation, and what interesting quantities do we get? I'm showing here the electron Boltzmann transport equation, where you have that the time derivative of the electron populations is equal to a term due to the external fields that we currently do not include. So at time zero, basically our initial condition is a certain excitation. And the collision processes that are computed entirely from first principles. I'm showing here then the electron Boltzmann equation and the phonon Boltzmann equation. For the electrons, you have electron-phonon collision processes. For the phonons, you have both electron-phonon and phonon-phonon processes. Now, when you write it this way, the problem looks deceptively simple. However, the collision integrals actually depend on the electron and phonon occupations at the current time step. So this is really a large set of coupled integral differential equations, and their numerical solution is challenging. What we do is, first of all, we set up a regular Brillouin zone grids, a relatively fine one, typically of order 100 by 100 by 100, and we store the relevant matrix elements. And then I'm showing it here now for the electron-Boltzmann transport equation. When you write it in full, you see the challenge then is computing the collision integral in the right-hand side, which depends on both the electron and the phonon occupations. The first possible solution is that you keep the phonons in thermal equilibrium because they're a large heat bath. So at low excitation, there's a sensible approximation, and you only time step the electronic occupations. When you do that for a reasonable number of bands and K points, you end up with something of about up to 1 million coupled integral differential equations. And so solving them, and in particular computing this right-hand side, which as you see, this collision integral is a Brillouin zone integral at each time step, is the key challenge. What we do is we explicitly time step the coupled system of equations using fourth order Runge-Kutta with a femtosecond time step. And the way we evaluate the collision integral is by using a hybrid MPI plus OpenMP parallelization. What we do essentially is we find all the relevant scattering processes that conserve energy within a threshold, and then we distribute the pair of points that contribute to scattering over multiple MPI processes. Within each process, we use fast on-node operations with OpenMP to form partial collision integrals, which we then sum up to obtain the collision integral at each time step. And so it is this hybrid MPI plus OpenMP parallelization that allows us to efficiently do these calculations. Now, in 2017, we're able to apply this framework to studying excited electrons and holes in gallium nitride. Here, what we discovered is that there is an asymmetry between the cooling rate of electrons and holes. For example, at time 0, we set up the simulation where both the electrons and holes are given an initial energy that is about 1 electron volt of the band edge. And so then you time step the equations, and you see that the holes cool to the band edge fairly rapidly. And after about 80 femtoseconds, they're at the top of the valence band, whereas the electrons lag behind, and they take about 5 times longer to fully cool to the band edge in about 400 femtoseconds. Now, the key difference here is that the valence band is threefold degenerate, and there's a range of scattering processes for the holes, and so that allows them to cool faster, whereas because gallium nitride is a polar material, the key interaction for the electrons is with the longitudinal optical phonon. This is the so-called Froelich interaction. So the emission of LO phonons is really the dominant channel and essentially the only one for electrons, which justifies the relatively slow dynamics. This asymmetry in the electron hole cooling has practical consequences, as we have shown. For example, in gallium nitride light emitting devices, when you use them at high current, there's a known energy loss, which is called the efficiency droop, and essentially the efficiency of the device, which is typically made up of multiple quantum wells, starts dropping. The other thing that happens at high current is that the electrons start leaking out of the device. We have been able to link the slow cooling of the electrons to this process by showing that the typical inelastic mean free paths for the electrons is longer than the size of the quantum well. And so at high current, for example, they are unable to lose energy and thermalize within the quantum well and recombine with the holes to emit light. This mechanism that we proposed, the slow cooling of the electrons to justify the loss of efficiency, can also explain the temperature dependence of the efficiency group, which is known to get worse at low temperature, where the scattering with phonons becomes slower, so the electrons would have even longer cooling times. So how do we know that the timescales we compute are accurate, and how can we validate the interactions? And so I'll show this here for the case of gallium nitride. The simplest calculation one can do is computing electrical transport properties, which, as I've mentioned, is one of the focuses of my group. Here, what we do is we compute the electron mobility in gallium nitride within the Boltzmann transport equation framework. So you use the electron-phonon interactions and then the band velocities to obtain conductivity and mobility. Our computed mobility, as you see here, it's the blue curve, and it agrees with the highest quality samples, so the highest electron mobility shown in experiments. And so that guarantees that the electron-phonon interactions we use are sensible and accurate. And so this type of validation, which you can do for electron-phonon using electrical transport for phonon-phonon by studying the thermal conductivity, is something unique to this family of Boltzmann equation approaches, and it would be challenging in other first principles methods. Recently, we've been able to time step both the electron and the phonon Boltzmann transport equation all coupled together. That gives you access to the coupled dynamics of electrons and phonons. The idea now is that you end up with up to 1 million coupled integral differential equations with up to 1 billion scattering channels in each of these equations. And the part that's really challenging is including the phonon-phonon processes for the phonon. So these are the anharmonic phonons in which one phonon generates 2 at lower energy or vice versa. And you see here, this is a double integral in the Brillouin zone, and you need to include all the relevant triplets of phonon states that contribute. We used a similar scheme that now also pre-selected the relevant phonon processes, used parallelization to time step. It is computationally costly. And what is really interesting, though, is that we can still use a femtosecond time scale and so fully characterize the electron dynamics, but also go up to about 10 to 100 picoseconds, which is the relevant time scale for the phonons. We've been able to apply this framework to graphene, which is a 2D system, so the grids are a bit more forgiving than they would be in a bulk system. Graphene is a very exciting material, of course. It has been widely studied using ultrafast spectroscopies, so it's also a good place for validating this theory. In graphene, we model the excitation of the material with an optical pulse that creates excited electrons and holes. What is known experimentally is that they thermalize to a hot Fermi-Dirac distribution within about 10 femtoseconds of the initial pulse. And so we take that as our initial condition for the electron Boltzmann transport equation, whereas we leave the phonons initially in their ground state. Now, what happens when you solve the equation is that the carriers you see start cooling toward the Dirac cone in about 100 to 300 femtoseconds. And as they lose energy, now you're able to also see which lattice vibrations or phonons get excited. At short times, it is mainly the optical phonons due to their strong electron-phonon coupling that get excited. And then at longer time scales, the optical phonons start decaying into acoustic phonons over a time scale of 1 to 10 picoseconds through phonon-phonon processes. And at even longer time scales of 20 picoseconds or more, you can actually see the acoustic modes losing energy toward lower energy acoustic phonons, which ultimately leads to the material equilibration. So what we can do then is we can essentially reconstruct the full cascade from electronic excitation to how the electrons give out energy to the phonons, and then the phonons undergoing all their internal processes and ultimately restoring equilibrium in the material. And so this longer time scales of 10 to 100 picoseconds would be highly challenging to access with other first principle techniques. The other advantage is that you can directly track all the relevant scattering channels, because this is a momentum space picture, and so it lends itself naturally to this kind of an analysis. You can also get information about the dynamics of each individual phonon mode. You see here, for the 6 phonon modes of graphene, we're plotting the excess phonon population, so the time-dependent population relative to equilibrium. Now, at short times, as we've mentioned, due to their strong electron-phonon coupling, it is mainly the optical modes that get generated, and then they decay into acoustic modes. But for 2 modes, you see the ZA and ZO, there's a very slow rise that actually occurs over about 10 picoseconds. Now, these 2 slow modes are the so-called flexural phonons. So these are the out-of-plane vibrations in graphene. And you see their dynamics is very slow because their electron-phonon coupling is very weak. So the carriers cannot typically generate them directly, but they get generated through the slow phonon-phonon processes. However, as these phonons linger in the system, they prevent graphene from going back to equilibrium for a time scale of up to 10 picoseconds. And there's spectroscopic signatures of this flexural phonon bottleneck, as I will discuss momentarily. Once you have the time-dependent electron and phonon populations in hand, you can predict a range of spectroscopic properties and essentially try to predict the outcome of time domain spectroscopies and diffraction experiments. The first one I will show is transient absorption, which is widely used to investigate electron dynamics. And so here are a calculation of a normalized differential transient absorption is shown in blue, and it agrees with experiments shown in red reasonably well. In particular, we can capture the initial rapid decay of the carriers as they generate optical phonons. And then at longer time scales, you see there is a lingering signal, which we attribute to the slow rise of flexural phonons, which heat back the carriers. Another very interesting quantity that you can compute is the thermal diffuse scattering. So there's a range of diffraction techniques, for example, using electrons or X-rays, that give you a signal near the Bragg peaks of the diffraction, time domain diffraction spectra that essentially depends on the sum of the phonon occupations. And so this is typically plotted over multiple Brillouin zones, where Q here is the scattering angle of the incoming particles, and it corresponds to the phonon wave vector. The experimental signal sums over all modes, and so you cannot distinguish whether this is an optical or acoustic phonon that's contributing to the signal. And you see when you take the differential signal compared to basically relative to equilibrium, you get large peaks that are directly related to which phonon momenta are excited. In this calculation, this is the simulated result. We get very large peaks at the corner of the Brillouin zone, which corresponds to the optical phonons that mediate inter-valley scattering in graphene. There would actually also be a large contribution from the center for essentially intra-valley electronic processes, so small q phonons. However, it's not easy to see because in equilibrium, you already have a large population of acoustic modes, and so the different signal is small. Now, at longer time scales where all phonons are excited, now you see that essentially they span the entire Brillouin zone, and that's a signal that the material is essentially thermalizing and occupying a range of modes. What's interesting is our calculations can also predict which phonon modes contribute to the dynamics, and so essentially they can contribute to interpret the experiment, which lacks that information. You can also do structural dynamics. For example, you can occupy the phonons using the time-dependent occupation. So you can look at the dynamics early on, and then later where all the modes are occupied. You can look at things like the mean square displacement that grows as the system relaxes. Even more interestingly, you can simulate experiments that are becoming more and more popular, where people excite with either through Raman processes or through an infrared intense pulse. They excite selectively certain vibrational modes at time zero. Now, in some systems, this drives either a structural or sometimes even a quantum phase transition in the electron liquid. And here, within the Boltzmann transport equation approach, we can model that process as a different initial condition to our solution. So we can, at time zero, occupy a specific phonon mode and create a large excess while we keep the electrons in equilibrium at time zero. And so we time step, then you can access both what happens to the electrons and what happens to the phonons. In graphene, the electron contribution is a relatively small ultrasonic attenuation of the phonons, but you see actually the phonon excess population. So at time zero, you have mainly allophonons, then they start decaying rapidly into TO, transverse optic, and then in about like 2 to 3 picoseconds, they start populating acoustic modes, and only later the flexural modes. So this is an interesting tool because it is directly linked to efforts experimental efforts that people now are focusing on, for example, using intense hard X-ray pulses at the free electron lasers, but also in tabletop setups where, for example, people can drive even transient superconductivity or manipulate material properties for very short transients. So the last topic of my talk will be a discussion of how you treat the dynamics in materials where excitonic effects are strong. So as you know, if you excite optically materials like a thin semiconductor or an organic semiconductor or nanostructures or wide gap insulators, because of the weak screening in this material, the excitation leads to the formation of a strongly bound electron-hole pair. So due to the weak screening, the excited electron and hole interact and form a bound state called exciton. When you have bound excitons like you have in these systems with binding energies up to an electron volt, clearly you cannot treat the dynamics of the electrons and holes independently. Rather, you have to treat the dynamics of the bound exciton as a whole, particularly when you, for example, experimentally pump near the band gap, because then you have dominant excitonic processes. In the context of calculations on crystals and periodic system, the so-called Bethe-Salpeter equation, or BSE, is perhaps the gold standard to compute excitons. And so you can solve this Hamiltonian that includes an accurate account of the exchange and direct interactions between the electrons and holes. And by solving it, you can obtain the exciton energies for each exciton state, which I'm labeling with S, and also the wave function of the exciton, which is expressed as a superposition of electron-hole transitions. So this is solved in the so-called transition basis. The challenge, however, is that when you investigate optical properties, you typically care about excitons that are in the radiative cones. And so within, with center of mass momentum that is essentially zero. And that is the standard solution of the BSE. However, when you want to, for example, investigate exciton dynamics and exciton phonon scattering processes, now the excitons, due to, for example, scattering processes of the electrons and holes, will pick up a certain momentum. And then you have to solve this equation at finite center of mass momentum on a full Brillouin zone grid. And so that's challenging, and it's a highly non-standard calculation. In our case, through a collaboration with the folks from the Yambo code, in particular, Davide Sangalli, we've been able to access these finite center of mass momentum BSE calculations and couple them with our code to investigate exciton dynamics. The first step we have taken in this paper is to compute the exciton phonon processes, because now you have to look at the scattering of the electron hole bound state from a certain initial state with a given center of mass momentum into a different final state with a different momentum where energy and momentum are conserved by emitting or absorbing a phonon. I will not attempt to reproduce this calculation, but essentially by perturbing the BSE Hamiltonian with a lattice distortion, you can compute this, the probability amplitude for this process, which is now the exciton phonon coupling. And what it looks like is actually very interesting and partially intuitive. So you have that the exciton phonon coupling is a quantum superposition of all electron phonon and hole phonon scattering processes that conserve momentum. So for example, you have here that you can have that the hole stays unscattered, but the electron scatters, and you can compute the electron phonon coupling coefficients. But now these processes are weighted by the exciton wave function. And similarly, you can have electron unscattered and hole scattered, and this process is also weighted by the relevant exciton wave function. So this our perturbative derivation is consistent with previous many-body theory derivations, but for the first time, we took it, basically we took the step of doing this computational tour de force of obtaining the electron phonon matrix elements on fine grids and then the exciton wave functions and combining them to compute this exciton phonon coupling and then using them to investigate exciton dynamics in various forms. So let me wrap up this topic in the next 5 minutes. So the simplest thing you can compute perhaps is again the exciton phonon scattering rate or the relaxation time. And now I'm switching here to an exciton picture. So this is no longer a typical band structure. This is exciton energy versus exciton momentum. So you still see valleys because the exciton is stable, and we can map directly the relaxation time on the exciton band structure. You see here at low energy, where you can emit only acoustic modes, the relaxation times are longer. However, at higher energy, when the exciton can emit a longitudinal optical, so higher energy phonon, this process is faster, but it can only occur above this threshold because now you have to have a final state available for emitting a phonon. So we did this calculation, I should have said it earlier, we applied it to hexagonal boron nitride, which is a polar material. And so here, again, similar to gallium nitride, you have that the emission of a longitudinal optical phonon through the Frolic interaction is the key process. So for example, you see the strongest coupling is to longitudinal optical modes. And so above this threshold for emitting LO phonons, now the exciton can lose energy rapidly on a time scale of about 15 femtoseconds. This is the typical time scale, for example, for an electron in a polar crystal to emit an LO phonon, but now this is a conceptually different idea because you have an exciton that is relaxing to a different exciton state. One way to validate these interactions, which is also very interesting investigation in its own right, is to compute the photoluminescence spectrum. And in particular, this approach can capture the entire vibronic structure of the photoluminescence. And I'm showing here results on hexagonal boron nitride. Now, the idea is that in the beginning, you have an exciton which is outside the radiative cone. So it could have a large momentum, but then you have a phonon that scatters it within the radiative cone, and then it emits light. We can solve the Feynman diagram for this process and then derive this formula for the intensity of essentially the phonon-assisted photoluminescence. And then you find contributions from the various phonons, which essentially correspond to the well-known vibronic structure of materials, where you see peaks spaced at the various phonon energies. In this calculation, which is the computed results are shown in blue, can actually reproduce the experimental trends very well, both at low temperature of 8 Kelvin, where we find all the relevant peaks due to the optic and acoustic modes, and at higher temperature, we can accurately capture the line width from the various photoluminescence peaks. This is exciting because, for example, in defect emitters, which we're now trying to apply this method to, in defect emitters, one of the signature really is this vibronic structure. And so our hope is to extend this method to localize the emitters and then apply them to defects that are, for example, being investigated for optical qubits like empty centers or defects in boron nitride. The last two slides I will show are on the application of this method toward a fully, actually real-time exciton dynamics done entirely from first principles. And here we applied it to tungsten selenide. So this is a monolayer tungsten selenide. As you know, this is a thin semiconductor. It has a slightly indirect gap. Here, the top of the valence band is at the K corner of the Brillouin zone. And then you have another valley at the same point at K. So optical excitations typically form an electron-hole pair here at the corner of the Brillouin zone, but then you'd expect that the electron rapidly transitions into the lower energy valley, forming this exciton, so-called Q or M excitons with finite momenta, and where the hole still sits here at the corner and then the electron sits in a different place. Switching now to the exciton picture, this means that at time zero with light, for example, you could excite a bright exciton with no center of mass momentum, so at gamma, which corresponds to an electron hole at K. And then you could watch the exciton transition toward these lower energy excitonic states at M and Q. Again, to validate the interactions and the band structure, this is actually quite sensitive of the energy difference between the valleys. We can compute the time-dependent line width, and we get extremely good agreement with experiment. And then what we do next is we formulate a fully, the Boltzmann transport equation now for the exciton populations, where now we fully compute the exciton phonon collision integral on the right-hand side. You see now the F are the bosonic occupations of the excitons. And you can now time step it starting from an initial condition. For example, you excite optically tungsten selenide, and then you watch essentially how it decays to lower energy excitons. So what happens here, as I mentioned, now you form these electron hole pairs where the electron scatters at different valleys that are lower in energy. The slow process, however, is transferring the entire exciton to the other valleys. So tungsten selenide has two sets of inequivalent valleys. That process takes picoseconds, and it is very interesting from an experimental viewpoint because it corresponds to the depolarization of the valley degree of freedom. Now, in our simulation, and I will show you this video, you see that you form rapidly excitons at Q and M. Let me play this again. So the exciton as a whole is losing energy, but you also form very little exciton populations at K, which is the inter-valley scattering processes. So that process is fairly slow, and we actually have evidence that depolarization occurs through intermediate excitons, so the Q and M excitons, and that is why it's slow. We can even model which phonon modes are generated and are currently collaborating with experimentalists who have interesting spectroscopic evidence of the same processes. So to wrap up, I would like to again highlight our efforts to develop a what will hopefully become a community code for investigating electron phonon processes, transport, and in this context, ultrafast electron dynamics. It is a highly user-friendly code that is modular, so it's easy to implement new physics on it. It also uses convenient data formats. It has a hybrid MPI OpenMP parallelization. It already scales up to a few thousand cores, so it can be used in large computer clusters. And so with currently what is implemented of what I've shown today is the ultrafast electron dynamics with the nuclei kept in thermal equilibrium, but in the future we will add more of the physics that I've shown today. So to summarize, I think I've taken almost a full hour. I hope that I convince you that there are interesting theory and code advances using this Boltzmann equation formulation of the dynamics, where essentially you can use accurate interactions that you can validate through transport for electron phonon or optical absorption or photoluminescence spectra for excitons. And using those, you can get microscopic insight into electron phonon exciton dynamical processes and therefore help interpret exciting new experiments in this area. Of course, there's still a lot to be done. For example, what we regard as frontiers in this field are addressing the spin degree of freedom, also addressing the very short times, essentially the coherent dynamics. For that, you need to include the pump poles and essentially switch to a density matrix formalism. The hope also is to be able to address some of these phase transitions that now are so very interesting in experimental ultrafast dynamics. So I will stop here, and I will be delighted to take questions now and also in tomorrow's, at least in my time zone, tomorrow's Q&A session. Thank you.
Thank you very much. I clap on behalf of the whole participants. There are many, many questions. So let's start from the beginning. So the first questions regard the electron phonon interaction. So, and how you calculate it. So is there any analytical behavior in the electron phonon matrix that we can perhaps fit with the coarse K grid data?
So that typically happens when the form of the interaction is known, and it essentially happens specifically for the LO phonon in polar materials. In that case, you know, for example, that the matrix element goes like 1/Q, and if you did basically a semi-empirical treatment of the Frolic interaction, you would capture that trend. If you plot the coupling matrix element for a general state as a function of a phonon wave vector, typically it actually varies rapidly in the Brillouin zone and in a way that is not easy to predict. The reason is the electron phonon interaction is strongly mode dependent, and so you would need to have basically one such approximation for each mode. You can imagine a material with many atoms in the unit cell. That would be really hard to do. So if you try to parameterize it somehow, which is essentially the conventional approach that has been used for a few decades, it can be done to some extent, but you do lose significant quantitative accuracy, and you basically miss, you may miss important details.
Okay, thank you. So have you come across any cases where a perturbative approach for exciton-phonon interaction fails to describe the dynamics?
We certainly came across that for carriers, for transport, for example. One simple example could be an oxide like strontium titanate, but this is true of many systems that have Polaron effects. When the electron phonon interaction is strong, essentially the carriers form polarons, and so then you cannot describe the electron phonon, or as a consequence exciton phonon interaction in a perturbative framework, at least not in the weak coupling lowest order perturbation theory. So many oxides that have, the way you know is basically these materials tend to have a low electrical mobility at room temperature because the coupling with the phonons is strong. So low typically means 10 centimeters squared per volt second or less. That tends to be a polaronic material, and then you find clear signatures of polaronic effects. We have addressed to some extent this problem in transport studies, and I'd be happy to point to specific references for large polarons, so not self-localized. For small polarons, there's more work to do, but we have not yet tried to address it for ultrafast dynamics.
Okay, and then there is interest in the perturbo code. So what are the main differences between perturbo and EPW?
EPW obviously cannot be employed to study ultrafast dynamics, right? It has as a main focus transport properties. Well, one thing you can argue is that perturbo is very efficient, and we have shown that in our paper. So if you tried the two codes, you would notice a significant difference in performance, but that is not for me to discuss at length and try to discredit the other group. So there is an overlap between the two in the way, for example, they form the matrix elements and interpolate them. What we do is we accurately include spin-orbit coupling, as we show in the paper. That is not the case for the EPW code. We can treat both norm-conserving and ultra-soft pseudopotentials. We can compute Seebeck effect, mobility, and so on, and also have these routines for the ultrafast dynamics, which you would not find in the EPW code. What's interesting also is we have basically our developer branch is about 3 times the size of what's been released. So we have routines for electron defect dynamics. We have routines for the coupled dynamics of electrons and phonons. And so these tools we will release in the near future, let's say within the next year or so. And so these developments are unique to our code. For basic calculations, though, if you tried the two codes, you probably can draw some conclusions for yourself about the, which code is more convenience or performance, or which code allows you to go, for example, to large unit cells. In our case, we've shown calculations of up to 40 to 50 atoms in the unit cell. That's due to the unique format in which we store the data and manipulate it that makes these calculations possible.
Okay, thank you. So then there is another question regarding the Boltzmann equation. So regarding the light-induced phonon population and phase transitions, can Boltzmann equations be used to study structural phase transitions such as charge density wave or ferroelectricity?
I think if you have evidence that there is a phonon mode that essentially gives you the incipient transition, so the early stage of the transition, then you will be able to see signatures, for example, by solving the Boltzmann transport equation that you generate that mode. Then you could, for example, take the non-equilibrium phonon distributions and use them in a separate model to try to investigate the phase transitions. So it's not, I don't envision an approach where you just, hit the play button in your simulation and you can induce the full range of effects, but basically you will be able to get some physical insight into these processes.
Okay, so then there is a specific question about the hexagonal boron nitride. So in the theoretical phonoluminescence spectrum, there is an inversion of the spectral weight between LO and TO when temperature is risen, whereas this is absent in experiment. Do you have comments on this?
So the person who asked the question observes an inversion in a trend in this plot. So, what I can say, for example, is that if we match the experimental intensity for the optical modes, the intensity of the acoustic modes is underestimated. So that's something that needs more work, and we don't fully understand what is the origin. One thing is to capture some of these processes for acoustic phonons in particular, because they're low energy, you would need extremely fine Brillouin zone grids. But doing the finite QBSE calculation on those grids might be very challenging. So to some extent, there is that effect. There is, for example, in the experiment, you also see some overtones by combining optical and acoustic modes that is not present in our treatment. So there are some effects that are not captured, but basically the point here is that the main features are captured.
Okay, thank you. So I think there are many, many more questions, but I think we need to leave them for tomorrow, for the question and answer tomorrow. And I think it's better to stop here. So thank you again for the nice talk and nice discussion. And
yeah, those who asked those questions which could not be answered can perhaps try to remember them tomorrow.
yes, exactly. Yes,
Yeah.
yes. Since we are at the same time, so I think we can answer. And tomorrow we should have also more time for this. So thank you again. So we close this session here, but don't leave, because we now move to the first question and answer session of the workshop, namely the one regarding this morning talks. I mean, this morning talks in European time. So Claudia Draxl and Geoffrey Hautier. So who I believe. Yeah, they are here exactly. So I will now cancel all the answer that were done to Marco Bernardi, and we now switch to the question and answer session. So okay, so let's start. I mean, if somebody has questions, please post them in the question and answer section. If
someone prefers to talk, you can just raise your hand, and then we can switch on your microphone. So
yeah,
if someone
exactly.
prefers to talk rather than to write.
The session is more free, so we have time to also to interact a bit more extensively than before. So so maybe I start just to break the ice. I mean, the section is not the session is not structured, so we are going to switch alternatively to between Claudia and Geoffrey, depending on how the discussion goes, and maybe we can all talk together depending on what we have to talk about. So my question is about vibration effects at the interface. So you said temperature and vibration effects are very important. So, and of course, most of your talk was about including these effects in the calculations. So do you see a need for low temperature experiments then to help understanding and to interface more basic calculations with experiments? So.
No, I'm not muted. Definitely, yes. And I think, well, most of the effects are, or many of the effects are not mere temperature effects, but the 0-point vibrations are very important. So very often this effect up to, I don't know, room temperature, so really dominates all the all the findings. So that's why experiments at various temperatures, in particular also going down to low temperatures, would be very valuable.
Okay. So, and are there many people doing that, or is it quite rare that in this field people do this kind of studies?
I think it's quite rare. It's becoming more and more popular. So I think there's more experiments now doing band gap, measuring the band gaps as a function of temperature. There's a lot of new experiments going on, I would say. Of course, there's this classical work by Manuel Cardona and co-workers who looked at this very early on. But then somehow it got forgotten, but I think now people are really taking that up.
Okay, thank you. So there is a question by Hasib Ahmad, and I'm going to allow you to talk. So please ask the question yourself now. Wait a minute, if I manage to. Yeah, so you should be now able to talk.
Hello, can you hear me?
Yes.
Yes.
Okay, thank you. My question is from Dr. Claudia regarding BSc. So I have read a little bit literature about BSc and found that BSc, the Hamiltonian of the BSc contains a term which is we call exchange term, which is said to be repulsive in
Mm-hmm.
effect. So, and it's also called as local field effect.
Yes.
So in RPA, we don't call it local field effect in this way. So I was wondering that why it is called local field effect in BSc calculation.
Well, actually, we also call it, well, depending what you mean with RPA, but in the random phase approximation for computing spectra, we also call it local field effects. But anyway, I mean, the beta cell beta Hamiltonian has two terms, as you said. One is the screen's direct Coulomb interaction, and the other, which is attractive, and then there's these local field effects which are repulsive. And whether it's important or not depends on the material. So depends how important local variations of the potential and the density are. So to give you one example, if or in mathematical terms, it would mean that if you change or disturb the potential in a certain Fourier component, and it affects also other Fourier components in the density, then this term is important. This would be the mathematical impression. More, if let's say a physical one is that if you consider the wavelengths of light, this typically spans several lattice constants or so. And so in that sense, from a unit cell point of view, the electric field is more or less a constant, but depending on the wavelengths and the potential of the system, whether it changes very strongly within a certain region, well, I think this is what is meant with this. So if the local field, the potential varies very strongly, so to say, over a given size or length.
All right,
Okay,
all right.
thank you.
So,
yeah, sorry, you want to follow up on that?
okay, one more thing related to it. I also want to know that how the spin structure arises in the BSc formalism. Like we call it sometimes spin singlet or spin triplet states.
Yeah.
Like if we can somehow switch off the exchange term in the Hamiltonian.
Yeah, I mean, you have I mean, you have three terms basically. One term is just the direct interactions. So this would be the independent particle approximation if you switch off the others. Now, if you only include the direct term, then, or whether including the spin or not, you can get the singlet or triplet, because there is, depending on whether the spins are parallel or anti-parallel, you either have exchange or not. That, so you can capture this basically going from the singlet to the triplet by switching off this exchange term. In other words, since the exchange term is repulsive, that means that the triplet solutions are typically are more strongly bound, because the term counteracting the attractive part is missing. And depending now, in some materials, it doesn't make any difference. So then the singlet and the triplet have the same energy, but in other materials, this might have a strong effect.
All right, all right. And the one more thing, last question is about the calculation that I was doing. Actually, in my case, the static dielectric constant, which describes the vibrational components, vibrational part of the dielectric, for compound was pretty large. So I thought that this suggests that lattice screening might be important in the calculation.
Yeah, this is a very important point, right? Okay.
Yeah. So, but the BSc calculation that I did without any lattice screening was already very close to the experimental data. So, what I think, what can I conclude, or what this is suggesting? I mean,
I don't know how you included it. It's very interesting to know what people are doing. We also try things, and it's not that trivial. But we also see some materials that have a dramatic effect if you include it. So if the low energy spectrum is dominated by vibrations, and it really introduces some let's say increase of the dielectric screening, then it may have a dramatic effect also on the binding energy, because if the screening is enhanced, the binding energy is going lower, and this actually cures or would cure many cases where the beta-salpeter equation alone overestimates exciton binding energies.
Yeah, that is true. That is true.
But which material did you compute?
This is bismuth-based oxide, which acts as a photocatalyst, bismuth tungsten oxide. So.
And it didn't have any effect?
No, if we include the lattice screening, the spectra get shifted. But I'm just saying that without any lattice screening, the spectra was already very close to the experiment.
Okay,
And
I mean, there might be a second thing, because the screening not only affects the exciton binding energy, but also may affect the band gap. So, and you could have some cancellation of effects there.
Oh, I see. So you are saying that electronic band gap might also be shifted.
May also change by vibrational effects. Huh? So the electronic band gap typically is getting smaller, and that means you would have a redshift, but then the reduced exciton binding energy would cause a blue shift. And so it could be that at least to some extent, the two effects cancel each other.
All right. So I think that is good for me.
Okay.
Right. Thank you very much.
Well, let's add one more element. So could you please also say your affiliation, so that even
yes, I'm from Pakistan. I'm doing my master in physics from LUMS University.
Okay, thank you very much. So we now move to the next question by Babu Baijnath Prasad, which I'm now going to allow to talk. So please also say your affiliation.
Hello, am I audible? Hello.
Can you talk a bit louder?
Hello, can you hear me, Professor?
Yes.
Yes.
Yeah, okay. So I am Babu, and I am doing my PhD in National Taiwan University. And first of all, my questions to Professor Claudia, and thank you so much for such a nice talk. My question is basically about regarding the hybrid materials. So in hybrid materials, you talk about like putting organic and inorganic together and studying the interface. But my question is like, what if we put like two inorganic materials and try to study the interface, and in contrast with the application of solar cell, how can we decide that which two materials, I mean, we should take for efficient like charge transfer?
I think this is not so easy to determine, because I think the reason why people consider this organic inorganic. So one thing is, of course, that you combine the advantages that both materials have, or you hope to combine. The other thing is that they are typically weakly bound. So that's why at least you have an estimate somehow how these two materials would align with each other if you know the vacuum level. So, I mean, I showed that this does not need to be true. So it's very, very tricky, but at least you have a first guess at least. For inorganic materials, you would, in most cases, have also covalent bonds, and this would, of course, change the electronic structure at the interface completely. So I think it's not, at least for me, not so easy to predict what happens then if you just choose two materials randomly and tell in advance how they would behave. You can somehow think about what would be the lattice mismatch, but you never know, because they could be superstructures forming, and I would not dare to predict what's happening. So, and that's why I think basically people try a combinatorial approach, where they try to, at least in the 2D materials, people mix everything with everything and then see what comes out.
Okay, all right. Thank you so much, Professor.
Thank you. So let's move to the next question by Oluzami Odeyemi. So, okay, so you've been unmuted.
Yeah, thank you so much. This is Odeyemi Oluzami Ebenisa from Nigeria. I'm presently running my PhD on UNIBEN, University of Benin City. My question, if I'm not mistaken, from what our presenter has presented to us, he made mention of a strongly correlated material. Please, I want her to please shed more light on strongly correlated electron system. Please, I just want to have more information about it. Thank you so much.
So to whom was this question related? Was it to Geoffroy or to?
Is the question clear?
No. To whom did you ask the question? Was it a question to Geoffroy Wautier or to?
Oh, yeah, I want to be sure because I don't know, maybe I'm mistaking your lecture with the second one. Somebody made mention of a strongly correlated material. So I need more information about strongly correlated material, those materials that are strongly correlated. Thank you.
I don't know actually what the question is about, because I mean, the strongly correlated materials typically have a very strong Coulomb interaction between these electrons, and they typically arise in systems where the electron density may be low. So in, let's say, metals that have a very high electron density, correlations typically play less role than in systems with very localized states and localized character.
Okay.
Okay.
Yeah, thank you. Thank you.
Thank you. Then we move to the next, which is Manish Kumar. So please. Manish, can you?
Hello. So my question is to Professor Claudia. So I want to know how to assign the different peaks, like charge transfer peaks in the optical spectra that you have shown as first, second, third, marked as first, second, and third. Actually, I didn't follow the answer in the morning session.
Okay, so in the beta Hamiltonian, we use this is a two-particle problem. So in order to solve this, we start with a ansatz for the wave function, in the sense that we take all possible combination of valence and conduction states, which would present, so that the valence states would represent the hole and the conduction states would represent the electron. And so we use a linear combination of all these possible electron hole pairs, or combinations or product combinations of valence and conduction states. And then by minimizing the Hamiltonian or solving the Hamiltonian problem, we get out the different excitations. So each of the solutions of this Hamiltonian is such an electron hole pair, right? So it has an energy and it has a wave function. And so if we pick one of these solutions, then we can analyze the wave function. And it tells us which of the bands contributes to this excitation. So we just map it then onto the band structure like I have shown. And I can tell, for instance, that in typical SP semiconductors, typically I would say the hole would sit on the conduction band, on the valence band maximum, and the electron could sit on the conduction band minimum. However, it could be that a lot of different bands and a lot of different K points in the Brian zone contribute. And this depends very much on the solution, right? So you can scan all these different excitations, and then you analyze which of the original valence and conduction states and which of the individual transitions between them contributes to one exciton. And in that sense, and then you can also plot it. So one is the analysis in terms of K-space. You look in the Brian zone, which of the transitions contribute. And the other analysis is that you just plot the electron hole wave function. So you, for instance, choose a point in space for the hole and then see how the electron is distributed around, or you choose a space in point in space for the electron and see how the hole is distributed around this. So in that sense, you get some idea how an exciton looks like in terms of band contributions in K-space or in terms of real space contributions by visualizing the electron hole pair wave function.
Okay, okay, thank you. I am from IIT Delhi, Indian Institute of Technology, Delhi, India.
Thank you. So the next question is by Javier Montoya. So I will allow you to talk now.
Hello, here is it. I hope you can hear me. Well, good evening, Dr. Draxel and Dr. Hautier in Europe. I had one question for each of you. First, for Dr. Draxel, I would like to know if the atomic configurations where you depict the properties that you calculate for the excited states correspond to ground state atomic equilibrium positions, or it is an additional piece of the puzzle where you have to, on top of every other ingredient that you consider, also allow the atoms to relax following forces that may appear after an excitation occurs.
Yeah. This is a very important piece of this puzzle, to be honest. So because if you redistribute the electrons, then of course they may relax into a different geometry. And this problem, I think, is not so critical in inorganic materials where you have pretty much stiff bonds. So it may play a role. So we also have these polaronic effects and whatnot. But it's more critical in the organic part because molecules are more volatile, so they may really relax upon excitation. That's why in chemistry this is a very important field. In physics, it's just up and coming because we more and more introduce vibrational effects on all levels. And this not only concerns the excitations, but also concerns geometry and also the geometry in the excitation. But it's not an easy task because there's one paper from several years ago, actually, about forces in the beta-sal beta equation. But so far, nobody has followed it. So this was from Stephen Lewis group, and well, I don't know at the moment the name, but it was one paper, but nobody has followed this. So to compute the forces in the BSE, we're trying something else. So we have actually used the constraint DFT to get relaxed position of the atoms in the excited state.
Thank you very much. And then for Professor Hautier, I was wondering about the database that he uses with over 40,000 available structures. Are those details about the structures accessed through an API, or is it some type of data mining that you have to do directly on the web page?
Yeah, so the materials, I mean, thank you for your question. I was referring that the data we use for most of it is on the materials project. And so the materials project can be accessed through a website. I mean, that's just browsing, but can definitely also be accessed with an API, which is linked with Python. And this is a REST interface. So REST is some protocol to access data. And this is good. This is go through HTML actually. So it's really easy to do. And so if you go in practice, what you can do is if you use, for instance, Pymagen, and in Pymagen there's something